start recording. Okay, so let's get into the lecture. All right, the agenda for today is I want to talk about the online classroom setup, recap on last week. We're gonna summarize some data, and I have suggested readings and homework, and if you're up for it, I have examples and applications for you as well. All right, so for this online classroom setup, I just showed you how to turn off sounds and banners for notifications. I did not know that you guys were still having those sounds and stuff because I turned them off on my end and I thought it would apply to everyone, but clearly that was not the case. Okay, so just turn them off yourself. Also, there's a lot more activity in online classes than in-person classes. Like the chat is so active, which is fantastic. But for me, it's really hard to keep up with the lecture and with your questions at the same time. So once again, a TA will answer your questions. So thank you, Tianrun, for being here. I will not check the questions as often as last class because I found that it interrupted the flow of the lecture like pretty severely. So ask your questions, and if they're not answered, then save them for the discussion board or for office hours. I'm going to try to keep lectures to 2 hours and the last hour for questions, so you don't have to be here for the full 3 hours. And moving on to an online environment comes with its challenges, so I will try my best to work through them with you. Also note that it is my first time teaching this course as well as the other instructors, so both of us are working hard to build our slides and stuff, so please be patient. We will post the slides and materials as soon as we can. Okay, notes on course logistics. About R, I just wanted to clarify that you will not be asked to write any R code in this course. I may ask you to modify a very small bit of the code, like maybe one word in the code, but even for something like that, I will walk you through it really, really quickly. And I will provide a lot of examples and guidance leading up to this point. My priority for this class is the statistical theory because it is a stats course, not a programming course. All right. And I don't expect any coding experience or statistical knowledge. That's what you are here to learn. You're here to learn stats. And you will use our Markdown as a tool, but this is not a computer science course. Lecture slides will be posted before lectures, but be patient. It takes a while to make them. As for Piazza, okay, I'm going to share my other screen with you now. So let's see. Share application or screen. Okay. Actually, let me just leave this. I will show you how to access Piazza. So let's say I'm in incognito mode, right? That means I'm not logged into my own stuff. What you want to do is you want to go to piazza.com/class with capital letters. And then once you're in here, what you're going to do is you're going to type in STA220. You should see this. Click on it. And there's my name. That is our course. So enroll. Okay, enroll as a student. I noticed that a lot of people still are not enrolled. There should be roughly 350 of us. So 150 is definitely not enough. If you have questions about this, post them. You can ask during office hours or something. Okay, and then as well, our Studio Cloud. There's a link here. Just click on it and join. It shouldn't be too bad. And for anyone who's wondering how to access the lecture recordings, what you're going to do is you're going to go to Quirkus, EB Collaborate, and then this takes a while to load. Over here in Sessions, see the very top left, there's like a hamburger button with the 3 horizontal lines. Go to Recordings. They're all going to be there. Okay, so Lecture 1 and Lecture 2, I made short recordings earlier. You can find them all here. Okay, enter full screen. So I first want to recap on last week. First of all, let's do a poll and see what everyone thought of the quiz. So there are 3 numbers. What do you think of the quiz? 1, 2, or 3? 1 being easy, 2 is fair, 3 is hard. Okay, sweet. So a lot of you did think it was pretty fair. I try to be pretty fair. Oh, I guess I didn't show it. Um, okay, anyway, most of you thought it was pretty fair, and I thought you guys did really well. So no worries there. Once again, the quizzes are not supposed to be like trick questions or anything. They're really just there to be like, did this person attend lecture? And it's also good for you to know if you understood things throughout the lecture. Most of you did really well. So introductory terms that we went over were sample versus population. A sample is a subset of population, right? So if I'm interested in Canada, I probably cannot get data from the entire Canadian population, which is why I will probably just sample or pick out a small group of people from Canada, and hopefully it will be a representative sample, as in the people in my sample are good enough to represent the entire Canadian population. A non-representative sample would be like all kindergartners in Canada, because not everyone in Canada is a kindergartner. Okay, what is a statistic? You should know that by now as well. It's a number that you calculate from your sample or from your population. Types of data, there's numeric data and there's categorical data. I'm going to be going through this fairly quickly since we already went over it last lecture. We have the mean, which is basically average. We have a median, which is the middle value. We have a mode, what appears most. And the mean, again, it's very easily influenced by really big numbers or really small numbers, basically outliers, right? So to mitigate those effects, we can use a trimmed mean, where you take away the biggest numbers and the smallest numbers on both ends. And then robustness is how sensitive, or the opposite of sensitivity. If your statistic is heavily impacted by extreme values, then your statistic is not robust. Okay, if your statistic is not heavily impacted by extreme values, then your statistic is robust. So just for intuition, when you think of robust, think of like a really like buff person, or think of a really like strong machine, like a really big bulky machine, a very robust machine, right? If you push it, it will like barely move. That's the same with your statistic. If something is robust, it isn't sensitive to changes. In this case, if I'm robust to extreme values, then extreme values don't change me that much. Okay, then there's also the 5-number summary, which includes the minimum, Q1, Q2, Q3, and the maximum. Now with quartiles, we spent quite a bit of time going over how to calculate them last week. And I had questions saying like, oh, my calculator gives me a different value. And like there are different things on like the internet, right? And that's true. Like there's so many different ways to calculate medians and quartiles. There are actually 4 common methods that people use, and these can give you different values. All right, so just as an example, the method that R uses in its quantile function is what I showed you last week. And I did that because I wanted it to be consistent with whatever R is going to give us. However, I do realize that that was a lot more complicated than the other options out there. So you can use other methods if you would like. All right, so another method is to split things in half first and then split them in half again. So the first time you split it, you get the median. If it's between 2 numbers, you take the average. So the median here would be 7.5. And then with the remaining values on the left, you take the middle of that to get the first quartile. And then everything on the right, you take the middle of that to get the third quartile. That is a method that some people have used. I've added the link here if you want to look at it. There's also another method that people use. So to get the quartile, the first quartile, you take how many terms that you have, you add 1, and you divide by 4. And that gives you the position for your quartile 1. And if it's like a number 0.5, then you're just going to take the average of 2 numbers. Okay, so there are more details here if you want to look at that. basically what I'm going to do is I'm going to accept whichever method that you want to use, because there's no like fixed convention of which one's the best method to use. All right, and I will not penalize you for choosing like this, this, or this. It's up to you. So which is the correct method to use? If I ever ask you to calculate quantiles, using any of the valid conventions will be accepted. All right. As for box plots, I will give you the box plot, and I will ask, if I ask you to interpret it, you just have to interpret it like this. This still holds. All right. The box plot still has a median in the middle. The hinge on the left is the first quartile. Hinge on the right is the 75th quartile, and the distance between Q1 and Q3 is called the interquartile range. The left whisker and the right whisker can only go up to Q1 minus 1.5 times the interquartile range, or Q3 plus 1.5 times the interquartile range. And everything outside of that whisker that the whisker doesn't cover are outliers. All right, so box plot. It contains the 5-number summary, and it also shows you the interquartile range. This is important, and it was on your quiz, so you should have that by now. There are 2 types of box plots, the modified and the unmodified box plot. The unmodified box plot has whiskers that extend all the way to the max and min. So if I go back, it would actually go all the way up to here, and it would go all the way up to here. But for our class, I will mostly use the modified box plot, which has whiskers that extend to at most Q1 minus 1.5 times the IQR and Q3 plus 1.5 IQR. Okay, and modified box plots are good because they show the extreme values very visually. And then we also had questions on why do we divide by 4 for quartiles? If you think about quartiles, right, just think about quarters, you break things into 4. And X% quantile is a number, so that X% of the data is smaller than that number. So just as a demonstration, the 10% quartile, or the first 10 quantile, notice it's quantile, not quartile, right? This is the number below which 10% of our data lies. The 20% quantile, or the second 10 quantile, is the number below which 20% of the data lies. 10 quantiles are called deciles, so the 10% quantile is the first decile, and the 20% quantile is the second decile. And then similarly, 1% quantile, or this should be first, that's a typo, or the first 100 quantile is the number below which 1% of our data lies. The 67th quantile is the number where 67% of our data lies under it. And these, if I break the 100 scale into 100 pieces, right, each one is called a percentile. So the 1% quantile is the same as the first percentile. And then finally, for quartiles, right, they basically cover 25% each. So the 25% quantile, or the first 4 quantile, is the number below which 25% of our data lies. So 4 quantiles are called quarters because they break the 100 scale into 4. And the 25% quantile is the same as the first quartile. Measures of spread. So I actually had a typo last lecture. There are 2 different types of variances. If you have all of the information for your whole population, then you are able to calculate the variance of that population. Then the variance is calculated as follows. Variance of your random variable x. So let's say you're collecting data and you're naming that variable x, right? That is denoted as sigma squared. So sigma is a Greek letter, and it's equal to the sum from the first observation to the nth observation, right? You're going to take them, subtract the true mean of that population, square each one, add them up, and divide by however many you have in the entire population. All right? And typically, we don't know what the true mean is, so we usually are not able to calculate the population variance. right? However, if I give you a data set and I tell you that the observations in this data set represent the entire population that I'm interested in, then mean, which is the population mean, is exactly the same as that data that I gave you. Okay, then in that case, you can find mu and you can calculate the population variance. So this is called mu. It's a Greek letter denoted, well, it's spelled mu. And then if you don't have population information, then in your sample, you can calculate the sample variance. It's denoted S squared. And it's very similar to variance, except you take, instead of the true population mean, which you don't know, you take the sample mean of all of your data and you also divide by n minus 1. So why do we divide by n minus 1? It has to do with the properties of large samples. Like if we have really, really big samples, when you divide by n minus 1, it actually converges to the true variance. So it's like a mathematical property. But also think of it like this. The spread is kind of like how uncertain you are. If you have the full population, then you're not that unsure, right? But if you don't have the full population, you're using your sample to kind of estimate the population's variance, then you should make it like slightly bigger to show that you're uncertain. So by dividing by something like slightly less than n, right, you can get a larger sample variance, which kind of is like, which kind of shows the uncertainty that you have from the sample variance. All right, so very similar, except for sample variance, you don't have the true mean, so you subtract the sample mean, and you divide by n minus 1. And higher variance means more spread. Similarly, for standard deviation, okay, standard deviation is just a square root, so instead of sigma squared, it's sigma, and instead of s squared, it's s. And higher standard deviation means more spread. Shape of the data, so by now you should know about symmetry, skewness, and modes, and ways to visualize things. So, okay, first of all, when we look at this slide and you see code, don't panic. I added it there just for anyone who's interested. If you are not interested / not comfortable, just ignore the code. It's totally optional. Box plots visually display the 5-number summary and possible outliers. So remember from last class, we had data on number of jobs held. Okay, we have the minimum, median, etc. And we can just turn them into a box plot. That's one way to visualize things. And here I added an outlier. Because we have an outlier, the whisker does not extend all the way. We can also have histograms that divide the full range of your data into smaller sections of equal length. So for example, if I have this data on the number of jobs held, then I sort it. The range of my data is the maximum, subtract the minimum, which is 12 minus 1, and that's 11. Now, knowledge check. Is the range robust to extreme values? So let me make a poll here. Yes or no? Is it robust? And remember, robust means that if I have an extreme value, it doesn't affect my statistic that much. Okay, so I see the response is coming in. All right. So it looks like most people said no, and you would be correct. If I have a really extreme value, right, that means that, I have either a really, really big value or a really, really small value. That would mean that either my maximum or my minimum changed, and that would directly affect my range because the range is the maximum subtract the minimum. So good job. To graph this, basically I can split my data, like split the range 11 into equal parts. Or because 11 is not a really pretty number, I can just go from like 0 to 12 or 0 to 15, whatever I like. So let's say I want to divide this into 6 sections. We call these sections bins in a histogram. All right, so this is the histogram. We have between 0 and 2, we have 1 bar that goes up to 1, and that's because one observation fell in the first bin. And you will notice that I use like a curly bracket or a round bracket and a square bracket. Round means that it's not inclusive, so 0 is not included. 2 is included. And here 1 is between 0 and 2, so we have 1 observation here. In the second bin, between 2 and 4, I have 1 observation, which is 4. And for example, between 4 and 6, we had nothing between 4, 5, and 6, so that's why it's empty. And the rest is pretty much the same thing. We can also change the number of bins. So once again, our code is optional, so don't freak out. I'm just showing you that you can change the number of bins. So if I don't like having 1, 2, 3, 4, 5, 6, I can make 1, 2, 3, 4, 5 bins. I can also make 2 bins if I'd like. And then if I add outliers, it looks different, right? So it kind of bunches everything up to one side, and then the others here. Without the outlier, everything's pretty spread out. So this data here is exactly this data, and the outlier just made everything bunch up together. Okay, and now we're going to visualize categorical variables. I'm just going to check the chat for 1 second. Okay, I think we're pretty okay. Talk slower. Yes. All right, so bar charts. Bar charts, I'm sure you've seen before. So basically, you just make a bar for every categorical variables. Yeah, you guys don't have many of the slides because I updated the most. All right, so I have 133 slides here just because whenever I like make a transition, if I just add like a sentence, that counts as another slide. In the PDFs, it's not the same. Okay, bar charts. Let's say for my report card, or in the classes, let's say this is from a class, right? 8 students got an A, 15 students got a B, 4 students got a C, 3 students got a D. Then in my bar chart, A would basically go up to 8, B would go up to 15, and the rest is pretty straightforward. We can also make fancier bar charts using ggplot, and this is something that I just wanted to show you. Don't worry about the code once again. This is just to show you the different types of visualizations that we can have. So this is using one function in R, and this is using another function. You can see we have extra things like grid lines, etc. It's just a little fancier. We can also make pie charts, but I will tell you now that pie charts are not very commonly used in the professional setting. And this will probably be like one of the very few pie charts that you will see. All right, and now we're going to move on to this class's material. The reason I went through the other material a bit faster is that it was already in last week's lecture, so I didn't want to spend too much time on it. All right, so this week's material is summarizing the data of relationships between variables. All right, in addition to looking at one variable, we can explore the relationships between 2 variables. And remember that there's a difference between numeric and categorical variables. So let's consider all 3 possible cases. When we compare categorical and categorical, that's going to be different from comparing categorical and numeric. And that's also going to be different from numeric versus numeric. Okay, so first, categorical. When we consider the relationship between 2 categorical variables, we can't rely on numeric summaries beyond just the counts and proportions of them. So we can focus on frequency and relative frequency. what we can do is we can create a contingency table, which I will show you. It shows the counts or proportions for each of the combinations of the values, as well as row and column totals. When the distribution of one variable changes with values of another, we call them dependent. If the values of one variable have no impact on the other variable, then we call them independent. I will also go into this. So examples. Let's say I have this data on pet owners. So I have the subject number, their age, their height, their weight, what pets they have, if they're a male or female, and their income level. So two categorical variables in here are pets and sex, right? So how about we calculate the frequencies and relative frequencies? Okay. I'm like just repeating myself. All right, so with pets, we can count basically frequency is how often they appear. So if we go back to the last slide, pets, how many birds are there, for example? In birds, I see 1, 2, 3 birds. So the frequency of birds in my data is 3. The frequency of dogs is 1, 2, did I skip one? 1, 2, 3, so 3 dogs. And the frequency of cats is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 3 birds, 3 dogs, and 3 cats. And that is my frequency. Relative frequency then is how many birds I have relative to the total. So that means the relative frequency of birds is just 3 birds divided by the total number of pets that there are. If I take 3 divided by 15, that's 1/5, which is 0.2. Similarly with the rest. Also, note that there's also a total here. And the total relative frequency should always be 1, because if you sum up everything, you should get the whole data set back. Let's talk about males versus females. There are 15 observations in total, so I just need to count one of them. Let's say females. I have 1, 2, 3, 4, 5, 6, 7 females. Then I just take 7 and divide by 15. That gives me my relative frequency. I have 8 males, so that 8 is my frequency, and the relative frequency is 8 divided by 15. Also, my throat is starting to die, so if I talk quieter or slower, that's because my throat hurts. Okay. How can we make a similar table that combines information of both variables? So I don't want to just look at them individually now. I want to compare them. What can I do? I can build a contingency table. This is a contingency table. It's basically the same as before, except now we have rows and we have columns. So back here, right, we only had one variable in the table. And now we have 2 variables. We have both pets and sex. And we just want to count, let's say this contingency table is for frequency, right? What we can do is we can just count, okay, in our table, how many observations is, like how many people have a bird and are female. So if we go through, right, this person is bird and male, this person is bird and female. Okay, we have 1 so far. Go down, we have another 1. So in total, we have 2. Let's say we want to do like males with cats, right? Every single row here is an observation, so we just go row by row. This person has a cat and is male, so that's 1, it's 2, 3, 4, 5, 6. All right, so for that we have 6. What do we do if we want to do relative frequency? Let's draw it. Okay, so because I'm doing this on my computer, I cannot annotate. Like when I share a screen, I can't annotate. So I'm just going to tell you how to do it. Basically, to get relative frequency, it's how many of this, what's the proportion of this type of observation in our whole data set. So what you're going to do is you're going to take, for this observation, you're going to take 2 divided by 15 and just put it there. Take 1 divided by 15, 3 divided by 15, and so on and so forth. And then you just add up everything here, add up everything here, add up all the rows. Your total here should be 1. So yeah, I guess I didn't include it. But yeah, it's basically you just divide by the whole total of your data set. And this is optional. I just wanted to show you what a data frame looks like in R. So back here in our Excel data sheet, right, you will probably see something like this. But in R, how the R reads it is as a data frame. Don't worry about this, totally optional. Another plot that you can use is a mosaic plot, and it's useful to visualize contingency tables. It looks like a standardized stacked bar plot. It's standardized because everything kind of makes like a square. Like in a regular box plot, right? You can have like, you know, this lower than another one, etc., etc. But here it kind of shows proportion and it all adds up to the same amount. This picture is from Open Intro, and you can read more about mosaic plots in the book. I don't think I'll be using it a lot in this course. And then marginal distribution. The marginal distribution of a categorical variable is the distribution of only that one variable in a contingency table. And it's called marginal. You can think of margins. Okay, we look at the margins of the table. So here, the marginal distribution of females would be not females, of sex would be, okay, there are 7 females and 8 males. We basically took the total, right, of this column and this column. For pets, the marginal distribution is 3 birds, 9 cats, and 3 dogs. Does this look familiar? So, okay, the distribution for this 7 and 8, 3, 9, and 3. So keep those in mind. 7, 8, 3, 9, 3. If we look back at just the frequency table, look at birds. There were 3, 9, and 3. And for sex, it was 7 and 8. Okay, so the numbers do match. We can also do side-by-side bar charts. So, for example, here we can have a chart for females and another one for males. For birds, we had 2, 3, and 2 under females, so that's why we have 2, 3, and 2. And then for males, we had 1, 6, and 1. I think this is pretty straightforward so far. Stacked bar plots. A stacked bar plot is when you kind of look at proportions. So here, for birds, for example, people who own birds, amongst people who own birds, I think it was how much? Let's see. Birds, males, it should be 1 out of 3, so this is roughly 33%. And females made up 2 out of 3, which is roughly 67%. All right, for cats, we had 3 out of 9 people who own cats were female. So that should be roughly a third. Red is female, so that's like a third. And so males would make up the other portion. And it's pretty similar for dogs as well. Same concept. Some examples from Open Intro are here. So for bar plots, you can also just put them right beside each other. This is proportions, so all of these add up to 1. Frequencies don't always have to add up to the same amount. You can read more about this in the Open Intro textbook. Okay, and in addition to marginal distribution, there's also something called conditional distribution. Conditional is, think of it as when you condition on something, right? So a conditional distribution of a categorical variable is its distribution within a fixed value of a second variable. So in other words, we fix the other variable. We hold it constant, we don't let it change. And the conditional distribution of A given B is formula A and B divided by just B. And this is going to look super abstract at this point, but let's go into examples. So let's say we only look at birds, right? So I filtered the table to only show birds. What's the distribution of sex when we fix pets to birds? If we look at it, right, we have 2 females and 1 male, so 33% are male, 7% are female. So here A is sex and pets is bird. If we go back, right, we count how many have A and B and how many have B. Here A is sex and B is birds. So I take birds as a denominator, which is why I'm dividing by 3. There's 1 male that owns a bird, so that's 1 divided by 3. There's 2 females that own a bird, so that's 2 divided by 3. What's the distribution of income level when we fix pets to be cats? Well, if we fix pets to be cats, then 4 out of 9 people make less than $30,000. 1, 2, 3, 4 out of 9 in total that own cats. 3 out of 9 make 30 to 60, and 2 out of 9 make more than 60. What's the distribution for different pet types? Right? So if I look at birds, 2/3 is female, 1/3 is male. For cats, 3 out of 9 is female, 6 out of 9 is male. For dogs, 2 out of 3 is female, 1 out of 3 is male. 2 variables in a contingency table are independent if the conditional distribution of one variable is the same for all values of the other variable. And as we can see, when we fix pets to be bird, cat, or dog, the distribution of sex is not the same, so pet and sex are not independent. And I want to elaborate on this just a little bit more. So let's say if they were supposed to be independent, like let's say they were independent, then the proportion of female versus male should be the same regardless of what pet is. And so that's what it means to be independent. If pet and sex are independent, then if I change one, it shouldn't affect the other, right? If they were independent, then I should have the same ratio throughout. And let's go back a few slides to that stacked bar chart. So here I have pets versus sex, right? When we have birds, we have a smaller proportion of males and females, but that changes when we look at cats. If these 2 variables were really independent, then basically the ratio of red versus blue would be the same for all 3 pet types. So that's what it means to be independent. I'm just going to take a quick look at the chat. Are you referring to marginal distribution? This is similar to marginal distribution. So you're basically fixing each one, right, and looking at the proportion of the other variable within each one. So if I look at bird, right, we have a ratio of male versus female. If I look at cat, we also have another ratio. And for dogs, we also have another ratio. Independence would mean that the ratio is the same for each pet type. And then now we're going to move on to Simpson's paradox. So here I have another data set. So I've collected data on people's heights and their gymnastic skills. And based on this scatter plot, it looks like when people get taller, their swim skill decreases. Do you think that is enough? Do you think that I can just end there? So let me do a poll. Is this enough? Update. Okay, let me just stop this and start a new poll. Um, all right, so I'm going to show the responses at this point. So some of you might have seen this little hint I put here. And this is going to be a little interesting. If I just look at these two variables, it might look like there is a decreasing trend. So I could, if I don't look any further, I might say, oh, if people get taller, they get worse at swimming. But actually, if I add age group, so red is everyone from 5 to 10 years old, and height is everyone from 70 to 80 years old, right? What we see is actually, if we look per age group, there's actually an increasing trend. So as people get taller, they actually do improve in their swim skills. But if we weren't to look at this, like if we didn't look at age group, then it just looks like there's a decreasing trend. So this is something called Simpson's paradox. Conditional distributions within subgroups can differ from conditional distributions for combined observations. Okay, so the conditional distribution, the distribution for height versus swim skill per age group is actually increasing, but if we did not look at it and if we just put it all together, then it looks like it's decreasing. So age group here was actually a lurking variable because the conditional distribution of swim skill was different when we considered age group. Okay, and here I'm going to a 10-minute break. That was actually pretty good in terms of timing, I think, because it's roughly an hour in. If you have questions, I will answer them in the chat. But we will regroup at 7:07. Okay. Can you repeat that lurking variable trend? Yes. So let's look at lurking variable. Simpson's paradox is like when I don't look at other variables, it might seem like there is some sort of trend, right? So here it might be like a decreasing trend. But that's because I'm not looking at another underlying variable that affects this. If I actually look at age group, the relationship between height and swim skill is actually positive. But because we didn't look at age, it just looked like it was negative. Which textbook is the homework from? The textbook is from Open Statistics. Open Intro Statistics. If you look at the syllabus, it's already there. When we talked about the formulas, so X bar can be lowercase. It doesn't have to be lowercase. As long as you know what data you're putting in, it doesn't really make a difference. Technically, capital letters mean it's a random variable, and data is a random variable, but that's not something that we've covered yet. So for now, let's just say there's no difference between capital X bar and lowercase x bar. Relative frequencies don't have to be expressed in decimals. They can be in fractions as well. How to find lurking variables. That's something that you kind of have to figure out. because I mean, it's kind of your job to be like, oh, what else could have affected this? And it's not always easy to find out what's the lurking variable. Okay, conditional distributions. Okay. So when I said this, I mean take all the observations where A and B are true and divide by all the observations where B is true. Okay, so B's next, B's. So here, for example, if I want to consider the distribution of sex given pets as birds, then I basically, A is sex and B is birds. So for males, what I do is I take everyone who's male and has a bird and then divide by how many birds there are. So here I have one observation, and then I divide it by how many birds there are, which is 3 observations. That's why it's 1 over 3, which is 33%. You can write this as 1 over 3. You can write this as 0.33. Similarly for females, so A and B, where A is female, would mean that I would have to look for females with birds. There are 2. I'm going to divide by 3. That gives 67%. You're right. This should be under numerical versus numerical. So I'm going to move this to numerical versus numerical. Don't understand how trend changes for short age. Doesn't it shift taller? Okay. The difference is if I don't look, okay, if I don't look at age group, then I can basically tell people, okay, if people get taller, their swim skill gets worse. But that's not true. What happens is that these values are lower than these values just because people got older. So for people who are like 70 or 80, they probably have like more health conditions, right? Which would naturally affect their swimming skill. But because we didn't see that, it just looks like when people get taller, they get worse at swimming. Okay, but when you actually add age group in, you see that if I consider age, like if I just look at people who are like 5 to 10 years old, it's actually an increasing trend. If for the same age group, if they're taller, they're better at swimming. The homework in the lecture 2 module is not to be submitted. That is not the homework assignment that is due on May 17th. So I'm gonna go and change that to suggested homework and make it so it's not for marks. How can we find the dependent and independent variables if the relative frequency differ both ways? Could you elaborate on that? I'm not sure what you mean. Marginal distribution, okay. Okay, so when I combine everything into one table, I'm basically counting pairs of variables. how many people have birds and are female? How many people have birds and are male? Right? But if I'm no longer interested in one of them, I basically don't need to look at it. So I just count the total females and the total males. This is the same as if I were to go back. Let's find that table. If I'm just looking at females versus males, this is kind of the marginal distribution. This, on the other hand, when I combine both of them, is called the joint distribution. And I will add that in. And don't worry, since I posted the slides earlier, I have made some changes. So I will upload the updated slides. When you say two variables are independent, does that mean no, there are no relationship both ways? Yes. Yes to your question of two variables being independent. So if two variables are independent, that means that they basically don't affect each other. If we graph the stacked bar plot and ratios of red and blue in each column differ regardless of which variable is on the x-axis. Okay, so it's not that one variable is independent and the other one is independent. It's their relationship. It's like if I were to talk about me versus you, it's not that I'm dependent and you're independent or the other way around. It's if we, the two of us, are independent. So independent kind of, you can think of it as unrelated. So let's say if someone gives birth to, if someone's pregnant, right? The sex of their baby probably has nothing to do with the weather outside. So weather and like baby genders would be independent. Okay, so let's regroup. We're gonna move on to the next part of the lecture. If you still have questions, just ask them at the end or during office hours or the discussion boards. Is my volume still okay? Okay, perfect. So now let's go on to categorical versus numeric variables. When we consider the relationship between a categorical variable and a numeric variable, we're going to take advantage of the numeric summaries of the latter, okay, because we can't really summarize categorical variables as nicely. We can take the numeric summaries of our quantitative variable, aka our numeric variable. They mean the same thing, restricted to each value of the categorical variable. And we will see what that means. So, for example, instead of just computing the average age of everyone in this class, I can compute the average age of females and the average age of males. Right? So here, our categorical variable is sex, so whether you're female or male. And the numeric variable that I'm comparing it to is age. So for every sex type, like male or female, I want, like, for example, the average age. And instead of calculating the median income of Canadian bankers, I can calculate the median income of bankers for every bank, right? So my categorical variable is every single bank. And for every bank, I'm going to find out like, oh, what's the distribution of the income? And we don't have to report just one number. We can report a whole 5-number summary. We can report modes. We can report means, whatever we like. So once again, let's say we're looking at this data on pet owners. Let's consider sex versus weight. So here, sex is our categorical variable, and weight is the numeric variable. You can build a box plot for each and place them side by side. So here's a box plot for females, and here's a box plot for males. And unsurprisingly, this is called, well, these two plots together are called side-by-side box plots. Okay, and what insights can we make from this graph? So maybe in the chat, just type in what kind of insights you see from this graph. Okay, there's a wider distribution of weight for males than for females. The weight for females is generally lower than males. Yep. Men are heavier, higher median, definitely. Females are lighter. Yeah. So these are all like valid insights from this. All right, so men are probably generally heavier based on this graph. The spread for them seem kind of similar. So notice that interquartile range for females is shorter than it is for males, so that part is wider. But females also have pretty large values that extend really far. They might just not be concentrated in those areas. They're more concentrated towards low areas, but there are some females who have higher weights, right? What if I want to know about skewness? The box plot doesn't really help with that, so a histogram might be more helpful. And here we can see in the histogram, in this case, it wasn't super helpful just because we don't have that many data points. There are like 8 females and like 7 males or something like that, so we can't see a pattern. But generally, a histogram is able to show you like distributions, whereas box plots are not able to. So the difference between the box plot versus the histogram is that if you want a really quick like 5-number summary, you can just use a box plot. But if you want to know if the data is actually like concentrated in one area, if it's left skewed, if it's right skewed, if it has like 2 modes, right, then a histogram is probably better. Okay, how else can you summarize a numeric variable? You can create a table. You can, go old school and make a summary table. What's the minimum of each? What's the first quartile of each? And so on and so forth. What about statistics regarding spread? So we talked about how one seems more concentrated than the other, and this is reflected in the standard deviation and variance. So in this sample, the variance for females is 239, and the variance for males is 268. So the weights of males do vary a little more. And are these results consistent with our observations from before, what we talked about before? Yes. This is kind of what we saw. What about age by pet? So back there, the concentration difference wasn't, or the variability, the spread wasn't as different here. But I wanted to show you an example of where the spreads varied drastically. So once again, in the chat, just let me know what kind of insights you can see from this chart. Oh, is it still frozen? It's still frozen? Oh, okay. Let me unshare and share again. Stop sharing. Can you see page 90? Okay. Okay, so let me backtrack a little bit. So back here, the weight was like the spread was not very different. They are different, but not super different. I just wanted to show you an example of when, okay, fine, 87. You can also go old school and just summarize it in a table. That's all I said. And then for spread, we can see that females are not as, like their weight doesn't vary as much as males. So the weight for males vary more, and this is reflected in the variance and the standard deviation. So the variance for females was 239, whereas the variance for males is 268. And these results are consistent with our observations from before. Okay, and I wanted to show you something where the concentrations differ a little more. What insights can we make from this graph? Actually, okay, answer this before I actually show you what I saw. So what insights do you see from this graph? Old people have birds, okay. Cat owners have more spread in their age, okay. Individuals who are 40 to 50 own dogs. Yeah, okay, so that's pretty good. It seems like bird owners tend to be a little older. There's the age of cat owners seems to vary the most. All right, it has more ability than the ages of both other pet types. The age of dog owners seems to be more concentrated, right, around like 40. Pet type and age do not seem independent because ages have different patterns within each group. Okay, these are not real numbers, I made them up. Okay, but back to the independence part, this is important. If age and pets were independent, right, that would mean that whatever pet I have, it shouldn't affect the age distribution. So the box plots, all three box plots should look similar if these two variables are independent. But because they are so different, right, these two variables are probably not independent. That means that, okay, if I'm older, I probably choose a different type of pet. Or if I have a different type of pet, or someone has a different type of pet, right? We could make like a guess of like how old they are, something like that. If these two variables are independent, that means they're not related, so we can't really guess what one is when we're given the other. Numeric versus numeric. When we consider the relationship of two numeric variables, we can see how one changes as the other one changes. How does one variable move when the other moves? We want to see how the two variables vary together. And so this measure is called covariance. Co as in together, and variance as in our regular variance, variability. How do they vary with respect to each other? And we have the following formula for variables x and y. So population covariance. If we have population data, then we can calculate the population covariance with this formula. So we're going to go from our first observation to our last observation. Take the x's, so x is one variable and y is the other variable. Mu x is the population mean for the variable x, and mu y is the population mean for the variable y. And n is the size of the total population of interest. Okay, so basically we multiply this and this together and we sum up all of those products and divide by n. And that kind of tells us how they vary with respect to each other. And sample covariance, when you don't have the full population data, right, is very similar, but once again, you just replace, because you don't know what the population mean is, you replace it with x bar. And because you don't know what the population mean for the other variable is, you do y bar. And similar to variance, you divide by n minus 1 instead of n. Okay, covariance. Covariance tells us how the two variables move together. If covariance is positive, that means that when one variable increases, the other one also increases. If covariance is negative, then one increases and the other one decreases, the other way around. The bigger the covariance, the stronger this effect. Right? So for example, if someone goes through a growth spurt, they're like, because they're growing, right? They probably are going to eat more. So they're going to take in more calories. So these two variables would have a positive covariance. And similarly to the situation with variance, covariance doesn't have a natural unit or intuitive interpretation of its magnitude. So last week, remember, someone asked why we use standard deviation even though we have variance. And the reason is that variance is like the squared of all your variables, right? So you like add, subtract, whatever, and then you square it. Now, if your data was in the units of like meters, now you're looking at meters squared, which is hard to interpret. So when we backtrack and we use standard deviation, we go back to our like original unit, which is how we can interpret it. Covariance is similar, it's hard to interpret, so that is why we use correlation. Correlation, you might have seen it as Pearson correlation or correlation coefficient. It's often denoted by rho. Okay, so this is a Greek letter. And it's just a covariance divided by the standard deviations of the two variables. So population correlation is the covariance of the population divided by the standard deviation of each, but I like to write it in my head. This is how I remember it. Just variance of both, multiply together and take the square root. That's the same as the covariance of both divided by the standard deviation of each. And here's just a different notation. Wanted to show you just like the different notations that we use. So sigma bracket of x stands for the standard deviation of x. Some people also write it as sigma and then subscript x. Sigma of y is the standard deviation of y. Notice that up here, everything that we use, the covariance and the variance, are the population values. Okay, so this is population covariance, and this is population variance, population variance. For a sample correlation, if we don't have the full population data, what we do is we do the best we can, right? So once again, it's the same formula, but now you're going to take sample covariance and divide by the sample standard deviation and the other sample standard deviation. And correlation only takes on values between -1 and 1. So a positive value means that the two variables are positively correlated. That means when one of them grows, the other one also grows. And then when one gets smaller, the other one also gets smaller, i.e. they move in the same direction. A negative value means that they're negatively correlated, so when one grows, the other one shrinks, or vice versa, and they move in opposite directions. So both covariance and correlation measure the strength of a linear relationship between two variables. Okay, so we're not looking at like quadratic relationships or like any other relationships. We're looking at linear relationships. The value of correlation of 1, for example, would mean that the variables are perfectly linearly correlated, and in the sense that a linear change in one is associated with a linear change in the other. The sign of the correlation or covariance describes the direction of the movement. So negative means that they move in opposite directions, and positive means that they move in the same direction. And the magnitude of correlation describes how strong that relationship is in terms of how close it is to being perfectly linear. Okay, one way to visually compare two variables is by using a scatter plot. So we're going to use our pet owner's example again. Right here, I'm just going to compare our two numeric variables, height and weight. So as you can see, it seems like as height increases, weight also increases. This makes sense. So what we can say is that they're positively correlated or positively associated, because as one grows, the other one grows as well. Okay. I've calculated the sample covariance for you. It's here. You could try it yourself. And we can also see the sample correlation, right? And look at our sample correlation. It's positive, meaning that they're positively associated or positively correlated. They move in the same direction. And it's pretty close to 1. So that shows that this is pretty close to being a perfect linear relationship. But we can't say that it's perfect, because perfect would mean that it lies directly on a line. Here I have another example. So I just made up some data for every x value. I'm going from 1 to 9, and y is just double of that value, right? Here I've calculated the covariance as 15, and the correlation is 1. That means they're perfectly correlated. Now, does a correlation of 1 mean that they're exactly the same thing, x is equal to y? No, it does not mean that. So here you can see x is not equal to y. In fact, y is always double of x. However, they're perfectly correlated because they're perfectly linearly correlated. If there's a perfect linear relationship, you can put a line there and it will touch all of the points. And note that the slope of the line does not affect the correlation, only the strength of the linear relationship does. So, for example, here, instead of multiplying by 2, I multiplied every number by 0.75. So the slope now is 0.75. Back here, the slope was 2. But it doesn't change the correlation. Okay, there's still a perfect line between the two variables. What it does change is the covariance. So back here, x is double of x, right? So every time x changed, y changed by like 2. So we have a large covariance here. But if I'm just multiplying it by 0.75, right, every change of x by 1 only changes y by roughly 0.75. So they vary together, but here they don't vary as much. So every time x changes, right, y also changes, but y changes by like 0.75, hence a smaller covariance. Back here, when we change the x by 1, y would change by 2, right? So the amount that it varies is bigger here, hence the larger covariance. The amount that it varies here is smaller, hence the smaller covariance. Here's just another example. They're not a function of each other. I just made random numbers. And here it's a negative relationship because as x gets bigger, y actually decreases. And you can see this in the correlation value. It's a negative value. And it's pretty strong. 0.94 is a pretty strong correlation. Next, let's move on to dot plots. Sometimes we might just want to look at one variable and plot the points of that variable. So we can use a dot plot. And the reason I'm showing you a dot plot after a scatter plot is just I feel like most of us have seen scatter plots more than dot plots, right? So a dot plot is just a one-dimensional scatter plot. I will be honest, I usually do not use this. We typically don't use this type of plot, but it's in the textbook, so it's kind of nice for you to just see. So in the textbooks, say from Open Intro, this was like interest rate from the Loan 50 data set, and they just plotted along a line, like the different values that they had. It's the same as a scatter plot, but with one dimension. You can also do a stacked dot plot, so points don't overlap. And this is especially useful for discrete numeric data. So like if you don't want all of these points to just fall down here, you can stack them on top of each other. And I wanted to say and make a note about causal relationships. So when you see something like this, let's go back here. You might be tempted to say, oh, the weight is higher, the weight causes the height to grow, or increasing height causes increasing weight. The issue with that is that it depends what kind of study you did. So back to this slide. There are two types of studies, an experimental study and an observational study. An experimental study is when you control your environment and you change things among your different treatment groups. So for example, if I'm running a weight loss program, or actually since a lot of you are from life sci, let's say I created a new drug, right? And I want to test out this drug in a clinical trial. If I would test out that drug, I am going to have people who take that drug and people who don't take that drug. But I want to control the rest of the environment. So I hold things constant, but I just make these two groups differ in that sense. For an observational study, I don't have that much control. Okay, so in an observational study, you just observe what's happening. So that's kind of like standing on a bridge and counting how many cars drive by, or doing a survey and asking people to fill it out. In these studies, you don't have that much control. And you cannot make causal claims from an observational study, because there are so many different factors that could have affected your results. You can't say that one thing caused another to happen. So for example, in the pet owner's example, you can't say that owning a bird causes people to be older. You can't say that people are heavier because they are taller, right? So you have to be careful. If there's a question in this course that says there's an experiment being run and people are controlling for different groups, then you can possibly make causal claims. But if I'm just giving you data and I said, oh, it's just some observational data, it's not an experiment, then you can't just make causal claims. What you can say is that there's an association between the variables, or that there's a correlation. And we're going to talk more about this later in the term when we talk about data collection and sampling and stuff. But I just wanted to tell you this because it's a common mistake that a lot of people make. When you see like a pattern, you just say, oh, thing caused something to happen, but that's not necessarily true. Okay, so you can only say that there's a relationship or there's an association. So by the end of this lecture, you should be able to choose appropriate summary statistics and graphical displays. So based on all the graphs that we've looked at, you should be able to know, like, okay, what's appropriate in this situation and what's not. You should be able to connect different graphical displays and connect summary statistics to the displays. So for example, if I give you a summary table of the first quartile, the median, third quartile, you should be able to see how that relates to the box plot. If I give you a histogram and it looks left skewed or right skewed, you should be able to tell me that, oh, okay, most of the data is concentrated to one side. Calculate appropriate summary statistics and construct appropriate graphical displays. So I will say you should be able to calculate summary statistics. The using statistical software part, I'm going to say don't worry for now. My priority for you is still the statistical component. And you will not be asked to code. So once again, to clarify if anyone came in late, in this course, you will be using R Markdown for your homeworks. And by that, I mean the homework will be created in our Markdown, and you will basically follow the instructions in that file and write answers as you would in like normal English. You won't be asked to code. You might be asked to change like one small word or one small line in the code, but it will not be as drastic as like writing a chunk of code by yourself. And all of this will be like, I will guide you a lot throughout the process. And then apply and interpret summary statistics and plots to learn about the data. So if I give you a data set, you should know what kind of summary statistics you want to use and what plots are appropriate. Keywords from lecture 1, this is just for you to, if you want to do a recap, you should be comfortable with these terms by now. So take a look at that. For lecture 2, we had some newer things. We had a contingency table. Mosaic plot will probably not be used as much, but it was in the textbook, so I just wanted to introduce you to it. Independence, and so on and so forth. I'll let you read through that. Now, as for suggested readings, the Open Intro Statistics textbook is in the syllabus. You can access it there. It's free to download, and it's super accessible. And then we also have the U of T STA220 Module 2, so just visit this website. It has some video recordings of other professors in the department. For your homework, and this is suggested homework, it is not homework 1 that will be graded. This is just exercises from the textbook that I think will help you with your understanding. Yes, the slides will be posted after this lecture. And if you are up for it, and if you want to try exploring some data, throughout this lecture, we've used the pet owners dataset a lot, right? And I already uploaded it to Quarkus, so if you want to take a look at it, you can. What I've been using in the slides is a shorter version of the full version that I created. So I also uploaded that if you want to look at it. You can practice summarizing the variables and seeing what insights you can derive from them and seeing what relationships you can find between variables. And another data set that you can look at is there's a tooth growth data set. This is a data set in R, and I provided an Excel CSV file for you on Quarkus. You can download it and play around with it if you'd like. It basically is a data set with like the length of teeth and seeing how different vitamin C or orange juice, if orange juice or ascorbic acid affected teeth. So you can play around with that, summarize the variables, and see what insights you can derive from them. And that is it. So in terms of R, I won't go over R today. My priority for you for this weekend, for Thursday, Friday, and this weekend is to go over these questions. And if you have time, try to work with like 1 or 2 of these data sets. All right. For our markdown, your assignments or your homework assignments will be in our markdown in the sense that I will have everything there and I will walk you through it. You just have to interpret the output. Like I will create like a box plot in R and I will just ask you to interpret it or something like that. So a lot of it will be like interpretation and stuff like that. No like heavy coding or anything like that. All right, so the material for this lecture is complete. I'm going to open up the rest of the time to do an office hour. Is there any way to see the solutions to the homework problems? I'm not sure if there are solutions to it. If you can find them, you can use them, but if not, I would suggest just collaborating with other people. You are not expected to do the homework questions before the quiz. So once again, for the quizzes basically test if you are paying attention in class and if you understood what happened in the lecture. The quizzes, like if you were comfortable throughout this lecture, you should be able to do the quiz like even at 9:01 p.m., like right after the lecture. Okay, so that is it for this lecture. I'm going to stop recording and just have the rest of the time to be an office hour.